Hello everyone, welcome to CYBR601, Introduction to Cybernetic Modeling and Simulation, Learning Activity 7, Agent-Based Modeling, Concepts and Applications. What we have on the agenda for today's lecture is we'll talk about agent-based modeling. We'll talk about the different topics, what is agent-based modeling. We'll also talk about the architecture as well as the terminology around agent-based modeling, which differs from numerical simulations, what we did last week. But the other thing too that we'll be talking about is just interspersing some readings that we'll be going through this week, which will be a little bit more substantial than last week. And then we'll also talk about a little bit about the project, the final project. And I think that'll just about cover it for our lecture today. So let's go ahead and jump into what we have today. And we'll go into the first topic, which is what is agent-based modeling? Okay, agent-based modeling is a computational model used to simulate a particular phenomenon, and this phenomenon can have, it can be simulating the behaviors and interactions of what we'd say is autonomous agents. And these autonomous agents can be, they have to be more than one for this to work. So in other words, for a agent-based model, there have to be an n plus one. It can't be just an n agent, and it has to be larger than that, so to speak. So agent-based models work well when we're talking about testing the interactions between agents. So it integrates some quite a bit of different, in terms of agent-based modeling. There's a lot in game theory. You actually see that a lot in large MOOCs, as well as massive online communities and massive online games and anything that's not, it doesn't even have to be massive. Let's say it's I know I go back to Bethesda games like Skyrim and games like Fallout. These are games that have simulated world models, where it's a really large world simulation with agents within it, non-player characters as well as the character itself. That would be considered an agent-based model, but it's a component of a much more complex simulation. That's a given. It's an agent-based model is a subcomponent within a game like Skyrim or Fallout or Minecraft, as an example. So that also includes things like complex systems, because again, a simulation, and especially with agent-based models, we're talking about modeling out complex interactions. It's not just like the numerical simulation, right? We can hammer out an equation for an n-body simulation between 2 bodies, 3 bodies. That's fine, but as we start to increase the number of entities, same thing happens here. As we increase the number of agents within an agent-based model, it becomes more than a human, any one human or a team of humans can manage. So there's a lot of different aspects to that, but yeah, high level, that's what an agent-based model. If you're interested in learning more about that in more detail, because there's graduate courses that are just focused on agent-based modeling, where it's just the whole course is agent-based model. So back to the theme of this course, just to remind everyone, we're providing cursory modeling and simulation expertise. I mean, we're going into some details, but as per what a graduate course is, we are diving into the details, but I also want to give you a breadth of what is out there and available. So this is one of them. And if you want to dive into the details of an agent-based model, there's some references here that you can certainly feel free to look into that. And those are very good readings, but I won't be quizzing you on those particular readings. Those are just good references to have in your back pocket. All right, next up. So I talked about we talked about entities. In this case, we're talking about agents. And agents are autonomous entities within a simulation. And what makes agent-based models different from other simulations it's really kind of it's it's different in a couple different areas, but in the numerical, let's just go with what we know today. Numerical simulations have a physics informed approach that is grounded in some kind of mathematical model or a mathematical equation. So in this case, the n-body simulation that we use for our numerical simulation, it uses gravitational Newtonian gravitational equations at its core to do the n-body simulation. And but that's not it. I mean, I guess you could kind of think of like that's kind of like an agent-based model, but it's from a different perspective. In other words, in an n-body simulation, the points in the n-body simulation that we're applying, so the point model, you could think of it as that those are agents within a system. And so yeah, but it's more an n-body simulation is more numerical than it is an agent-based model. And the reason that I say that, and here's the differentiator, is that an agent-based model, as you can kind of see it looking on the right, is it's more focused on modeling out, I would say, social and or biological phenomenon. It doesn't do it does it on a simple. There is an equation. It's a in this case a lot of agent-based models. They're algebraic, simple distance, Cartesian distance functions. So that's x minus x2 minus x1 plus, or I should say, if I remember it, but it's taking that, and then you take the square root of that, and then you're bringing in y1, or I'm sorry, y2 minus y1, and then that's a 2D distance function, and then so there's that kind of thing. I'm not looking to make everyone here to jump into the math, but what I'm saying is agent-based models work off of what's called a neighbor function, and that neighbor function can be different functions. It can be, and I'll talk a little bit more into the details on that one, but just know that a lot of times when we're talking about agent-based models, we're talking about the interactivity between either human analogs, animal analogs, corporate analogs. We're kind of looking at social systems, and or approximating social systems using an agent-based model. So that, just to give you an idea, that's how it differentiates between a numerical simulation. And you might be asking, well, can it be both? And you could absolutely say yes. And in any really advanced simulation, you're going to have numerical simulations, you're going to have agent-based models, you're going to have system dynamic models, you're going to have economic models, you're going to have hundreds of functions. And it's no easy feat to create a very immersive, expansive simulation, especially when you're talking about trying to approximate like real world interactions. So anyway, that's just something to keep in mind. So we're just isolating to agent-based models for this week. So let's jump into the different aspects of agent-based model. In this case, for an agent-based model, we're not talking cosmology this time around, but we are going to be talking about something that is a little bit more focused on something more close to Earth. In our lab, we'll be actually talking about how information spreads through a human ecosystem using an agent-based model, and simulating how that can spread. So to do that, agent-based models have a different set of terminology. So this is another differentiator, hint, hint, as it relates to your final project. Here's a differentiator that is phenomenon, environment, and agents. The terminology is different also, and that's because agent-based models, again, they're looking at things a little differently than numerical, actually a lot differently than numerical simulations. So let's jump into a phenomenon. What is phenomenon? So in this case, it's the what is it that we are trying to model, and this can be information spread. This can be product awareness. This can be anything where there is a linkage between agents within the model, like cell phone usage. That could also be something, right? That would be a little bit more complex agent model, because it would be a great agent-based model, because then what you're doing is it's not just human to human, it's human to phone and phone to human and phone to phone interactions, because the phones also are agents as well. It's not always just human to human interactions, but in this case, this is a simple one where it's just information awareness or product awareness, and and the phenomenon, that's the phenomenon, and then that leads to what does the environmental, so if that's the phenomenon, what is the environmental space? So in this case, this is where the agents behave. This is their playground. So when we create a simulated environment, the agents in this case are in a what we call a cellular environment. I've got a little typo up here. We are going to use a cellular environment for our lab. So I'll have that cleaned up for our lab. And then when I download this, or rather upload this lecture, that'll be cleaned up too. Anyway, so we'll be using what's called the cellular environment. So it's a cell-based neighboring algorithm, which makes the algorithm itself, again, we don't have to get into, we're not going to get into the detail. Just know that it's a simple linear algebra is what we're using. We're using a distance equation in a Cartesian plane, and it's a 2D Cartesian plane what we're using here. But with that said, agent-based models, more advanced ones, operate in 3D, right, in terms of their neighboring algorithm. So that means that there's not just an x to y, but there's an x, y, and z comparison between point 1 and point 2. So your distance function in a 3D is got a little bit more to manage, but also a cellular environment that's a 3D cellular environment, it could also incorporate a 4D, which is that over time, so simulation over time, which again, remember, simulations almost always iterate over time. So an agent and the environment are models. Right, the environment is a model, and the agent is a model within that model of environment. So this is something to just, I've talked about the neighbor cell, something to keep in mind as we move on to the agents themselves. So a word on agents, I have alluded to in an agent-based model, what are the agents? Well, agents can be anything. They don't always have to follow and be a human, as an example. They can be molecules, they can be bacteria, they can be animals, they can be machines, vehicles, robots, factories, countries. Agents can also be planets. The solar system can be an agent because it has an interactivity with its surrounding space. There's just all kinds of agent-based models can be whatever you want them to be. As long as there's what we'd say is there's an interaction between agents, then it can be an agent-based model. Okay, so the lab is going to have we will have two rules. So agents, one more piece of info, that agents have rules. That, in other words, and the environment also has rules. Remember, in our numerical simulation, there are simulation parameters. That establishes the rules by which the simulation operates, the environmental space. Agents also have rules. In this case, the agents, they can move in one of the neighboring cells, and they can influence their knowledge with other neighbors. And so in this case, there's a probability of P. So this is something to be kind of thinking about as you move through this course. There's another bit of terminology that I've been introducing, which is the idea of stochastic versus deterministic. So that's something to be keeping in mind. So in this case, which can be influenced with probability P, means that if you have any type of probability, that means that there is a strong possibility that the simulation and or the agents that you're working with have some kind of stochastic boundaries. It doesn't mean that the agent and or the simulation itself, in this case the agent and or the environment, can have it doesn't mean that it's fully stochastic. In other words, it's fully randomized. Usually there's a boundary. In other words, it's semi-stochastic system. So agent-based models, a basic one can be a static agent-based model. In other words, it's the movement and sharing of information within agents or interactions between agents is formulaic. And so in other words, there's it's strict logic, and that strict logic is deterministic, which makes the agent deterministic. And so there can be some interesting phenomenon that happen even in deterministic behavior. Even in deterministic behavior of sharing of information, their output can sometimes be probabilistic. So anyway, where I'm going is that's something to kind of keep in mind, is that agents, more advanced agent-based simulations have usually a mix of deterministic and stochastic elements. They aren't usually, a more advanced one isn't either or, it's usually both. Okay. So one other thing that you'll see in the lab when we talk about this is agents' ability to influence others depends on their knowledge feature. And so in this case, the knowledge feature, if it equals 1, it means the agent is aware of the product. And if the agent is not, then it's 0. And this has to do with the probability based on the neighboring algorithm. So if they're near and they happen to be near the agent, and it's the proximity. So that's really what we're saying, is that if two people are approximate to each other in terms of their distance, then it's probably a high degree of likelihood that they're going to, 1, influence each other through the exchange of information, and 2, influence each other through the tacit exchange of information. In other words, it doesn't always have to be like, I told you. You could have just heard it just by being in proximity. And that's very much a thing, right? So that's something to keep in mind as well. All right, I think we've talked enough about agents. Next up, we've talked about the numerical simulation architecture. Let's talk about the ABM simulation architecture. You'll notice everything on the right side is still the same. So in the middle, still the engine. It's still a computer hardware, operating system, and M&S software. And on the right, you have a simulation. We're using an agent-based model, and our agent-based model is going to be in the lab a human. It's going to be human analogs that we're going to be using. We're going to create up the exchange of information through a very, very, very simple model of a human and their interactions as they relate to simulating the exchange of information. And then the M&S software we're going to be using in the lab is going to be the same. We're going to be using Anaconda and Spider to show off that in both the follow-along lab as well as the UTry lab. The thing that's different in the simulation architecture here, and this is something to keep in mind for your final project, this is another area that you will want to be zeroing in on, is this modeling architecture is going to be different for an ABM in the sense that the concepts underlying it are different. So we use a neighboring algorithm in agent-based models. We use the terminology phenomenon, environment, and agents in agent-based modeling. If you're interested more on the military route for simulation architectures, one of the things that that you'll find is that agent-based models will take on a slightly different view and different terminology. It'll be, instead of agents, they'll use the terminology actors. So you'll hear that in the DoD world, depending on the type of ABM simulation you're doing. So if you're doing wargaming, right, back to game theory, because there is a lot of game theory at the heart of ABM simulations that influence ABM simulations, as it were. In the military world, you'll use actor theater. So the theater being the environment and the actor being the agent. So and here what you would say is the phenomenon is wargaming, let's say. In the DoD world, it's influence in wargaming, right? And then the environment, they would use what would be called theater. And then here they would say actor. So it would still be based on neighboring algorithms, and then there might be some other algorithms that they'd have for wargaming scenarios that isn't just always neighboring, but they're still very much strongly associated with neighboring algorithms. But anyway, that's something to keep in mind if you're simulating war games from an ABM war game simulation. Okay, but that also has implications into your final project. So when we get into, again, and I'll start to share this out here this week, later this week, you'll start to see a picture of what the final project's going to look like. But the conversations that I'm having here, where I'm differentiating between numerical simulations and ABM simulations, and the different terminology, right? The stochastic versus deterministic versus mixed. The idea of environment and phenomenon and the algorithm versus, the specific pieces and nuances between a numerical simulation and an ABM simulation. I really want you to dig through that in the final project. And again, there'll be more guardrails to be shared with everyone here, but definitely be on the lookout for that and be thinking about that and noodling on that as you go through the course. All right. So another review on, in a little bit more detail, because I know we've talked about this textually, but let's, for visual, I'm more of a visual person myself, this idea of algebraic distance and what that means. Well, what we're saying visually, this is what we're talking about, a neighbor. So if I've got a person in a particular square, and remember, we're basically in this case, in the program, a record is a person, and then we're maintaining a record, an index of that person, and we're creating a column within that of, did the person have awareness of the product, or do they not have awareness of the product? In this case, we're putting green on it. We're saying that in the case, anytime there's a 1, remember that's the rule. For the agent having 1, that means that they are aware of the information or the product. And anyone that it's in the that doesn't will have a 0. And that's the whole concept, right? And so the idea is that as information spreads and the neighbors change, right? That square, that cellular square of proximity, if you changed it to this person here, right? This person here, if you put their proximity, they're not going to have an opportunity to share. And that is the heart of what's going to happen. Whereas these two are paired very closely to each other, so they will have an opportunity to share. This person, although we don't have the cellular environment around it, if there was a person off to their right, they would have an opportunity to share, or be influenced by someone nearest to them. That's the concept of a neighbor, and it has a lot of applicability rather to agent-based models. It's a very big core of agent-based modeling, ABM simulations, as it were. Okay, next up is Mesa. There's a Python library, a Python ABM simulation library called Mesa. And there's actually a good 3 or 4 of them that exist in the Python world to do agent-based modeling. And they do it in different ways. Some can incorporate machine learning, which would be more of a stochastic view of the world as it relates to the terminology and I'm sorry, as it relates to the simulation architecture itself and the underlying behavior of the agents within that. Do they have stochastic behavior? In other words, are they more random? Or are they semi-stochastic, where they have some deterministic features, but they exhibit some stochastic random behavior oddities, which is probably more approximate to what humans are. And we can talk more about that down the road. That kind of is beyond the scope of this course, but in our machine learning autonomous systems undergrad and grad specializations, we'll definitely talk more through what that might look like in terms of that kind of topic. So anyway, we'll finish up with that, because I think that's plenty for what we're talking about here. So that wraps up more terminology. I want to review the lab here just to let you know we're going to be using Anaconda Navigator, and in this case, ABM. What kind of ABM will we be doing for the lab? Well, we're going to be modeling information dissemination, whether it's product awareness, whether it's a marketing campaign, whether it's let's say I'm trying to share a training, cybersecurity training throughout the organization. Well, that's information dissemination, right? And so I would like to simulate how that's going to happen. So that's what our lab is going to focus on today, this week. Again, why ABM simulation? Well, it's important. One thing to keep in mind as it relates, and this is a common theme, and this is back to our project, right? You have different simulation types: live, constructive. There's different virtual, right? Virtual. This is a virtual simulation, and not only is this ABM a virtual simulation, but the fidelity of this simulation is very low because we're essentially taking humans and abstracting them into a record or a point particle, in a point within this simulation. And the reason is we can actually, that gives us a lot of, the low fidelity gives us a lot of breadth. In other words, because it's so, if we're taking humans and abstracting them into a point particle model, in this case, it allows us to do millions, billions of interactions on the cheap. Because we are keeping the model fidelity low, it means that we can spend or expend more computational resources on broadening out the simulation. Now, in this case, we're not doing that. We're not throwing more at it. We're going to keep it small and look at the interactions of a couple hundred. I don't even think it's that many, but we're going to be keeping the simulation small in the lab just to kind of keep it confined. What do we need for the lab? You need Anaconda, the Mesa library, which I'll show you what you need to do there. It's pretty straightforward. Spider, again, downloaded as part of Anaconda. You'll need my Python code. And then we've got another one called Conway's Game of Life. This is one that is actually something that you're gonna upload on your own, and you're gonna get it running. You don't have to do any coding. But it's a perfect example of an agent-based model that uses a simple algorithm. It's all formulaic, but and it's actually a deterministic. I will say this: Conway's Game of Life is a deterministic agent-based modeling simulation. But what happens out of Conway's Game of Life can create, even through deterministic behavior. It can create interesting emergent properties that are pretty complex. So anyway, it's very famous, Conway's Game of Life. There's a lot of, again, we could have a whole class on just Conway's Game of Life. But again, we'll just keep it high level. What I want you to do, and I'll talk about this in the lab, is again, knowing and understanding the differences between all the different simulations and what's available to you. Comparing and contrasting is going to be a big part of the final project, but that's also what I want you to do this week, is comparing and contrast between the follow-along and then the follow-along lab as well as the U-Try lab. Okay, I think that, one last thing. I've talked a little bit about this already. I'm almost done. I think there's one more slide after this. Analyzing labs. So just be on the lookout for this. I've hammered this, deterministic, stochastic, mixed, I think you can be assured that I'm going to continue to talk about these topics because they do, especially for the machine learning and autonomous systems students. Having a healthy understanding of this is very critical to understanding how to implement architectures. And so that's why I'm hammering away at this. Be on the lookout for these as you're thinking through the architectures. All right. So labs, talked about that. We've got two labs. We got the follow-along ABM simulation. That's going to be a information dissemination. So that's going to be what we're going to be focused on for the follow-along. And also for week 3 labs, I've got Python, another Python. It'll be loaded up in your Canvas lab materials. But you'll also have another one. This one you will do on your own. I'll show you how to kind of approach getting Conway's Game of Life going. But after you get it running and you get it going, then I want you to ask yourself the following questions. What is the difference between Game of Life and the product awareness simulation? And what are the differences between ABM simulation and numerical simulation? So ask yourself those questions, and then I want you to it's probably a good idea at this point to start writing all of your thoughts down, even just informally. When you think about it, just sit down and go, what is the difference? And just, even if it's just some bullets, that's going to be huge and helpful. But start taking all these questions, and every time I ask you some questions here, just put 3 or 4 bullets down. What is the difference between Game of Life and product awareness simulation? From a stochastic versus deterministic perspective. What is the difference between Game of Life and the ABM simulation for product awareness as it relates to the phenomenon that you're looking at, right? So throw those in there, right? Compare and contrast from that perspective. Same with, what are the differences between ABM and numerical? Well, I gave you quite a few already. So put those in. Start jotting the notes down. ABM simulation is more focused on social interactions, ecological interactions. It's got, whereas numerical simulations are focused on physically informed simulations with a defined, emphasized physical mathematical formula at its core. So those are things, again, just throw those in there. All right, I think I've killed that. So let's move on to the next one. For this week also, I want you to read, this is why I kind of teed this up at the beginning of our lecture today. You want to read pages 9 through 28 in the simulation-based engineering handbook, the PDF that's uploaded. It's called Revolutionizing Engineering Science Through Simulation. It's a bit old, but it's very useful, very helpful, and it still holds today. It was put out by the National Science Foundation in 2006. Here is a copy of it. Let me show you right here. This is the PDF, simulation-based engineering science. It's available online. It's free. And what I want you to read through, again, National Science Foundation. And let me get to... see if I can get here to the table of contents. And I want you to read through the payoff part. So this is SBES in medicine, predictive homeland security, energy, environment, materials, industrial, and defense applications. And go all the way up to 28. So 9 to 28 in here. And then, of course, there'll be more readings. If you feel like you want to read through the rest of this, feel free. It's not a huge... handout, but it's definitely really helpful. This is diving into more details. NSF's got some great materials, but again, this is free and available. What I'm looking for everyone to get out of that reading is getting a better appreciation of the applications and benefits of modeling and simulation from NSF's perspective. With that, I am done with the lab. I'm with the lecture, and I will see you in the lab.